Hey, flipped chemistry, how you doing? You ready for another lecture? I know I am. Here we're talking about electron orbitals. Now, this lecture will pop your head, I promise, but you will get it. This is a little bit awkward. We're going to be trying to picture things in our minds as we talk about them, and sometimes the picturing does not really happen, but that's why we're going to do labs. So you can do models with this and put it together and hold it in your hand and be like, oh, now I get it. But for right now, we're generating something that you have on paper that you can use to build your models and reference back to and go, oh, that's what that meant. Okay, so right now, if you don't get it, it's okay. Jesus loves you. You'll be okay. Suffer through it and we'll make it happen together. Okay, electron orbitals. Everybody, take a breath. Here we go. Electrons arrange themselves in energy levels. We've already talked about that. And so energy levels are somewhat a definite distance from the nucleus. Now that's going to be accepted in a little bit, but on average, energy level 1 is closer to the nucleus than energy level 2. Energy level 2 is closer to the nucleus than energy level 3, and then 4, and then 5. And as the energy levels get bigger, just like rings around an onion, if you cut an onion, right around the core, it's small. And then as they get bigger, they can hold more onion, right? Same idea here. The energy levels that are further from the nucleus get bigger and can hold more electrons, right? So the total number of electrons in a neutral atom is equal to the number of protons in that atom. And you already know that. So carbon is element number 6, and it has 6 protons. That's why it's element number 6. But it also, if it's not an ion and it's not in a bond, it's just carbon being carbon, it has 6 electrons. So 6 electrons, 6 protons, 6 negatives, 6 positives, they go away into nothing. They neutralize each other. That's why a carbon atom is neutral if it has no other bonds going on, right? A higher energy level is further from the nucleus and can hold more electrons. So in the first energy level nearest the nucleus, it can only hold 1 pair of electrons, 2 electrons. And then as you get bigger, energy level 2 can hold 8 electrons. Energy level 3 is even bigger, it can hold 18 electrons. And if this diagram were to keep going, energy level 4 can hold more, energy level 5 can hold even more. So the bigger the energy level, the more electrons it can hold, the further away it is from the nucleus. Okay? But they're not round. I just showed you pictures that were round. I'm sorry. They're not round. They're all kinds of funny shapes. And so we're going to take each energy level, each average distance from the nucleus that electrons are, and we're going to divide them up into orbitals. Each orbital can only hold 2 electrons. How many electrons? 1, 2, 2. 2 electrons. And those electrons are going to be orbiting around in some not round shape. And they're going to be still in average distance from the nucleus. That's the same as the other electrons in their energy level. That's why they're all in energy level 1 or 2 or 3 or 4 or 5. But they're not necessarily following each other in a game of like tag around the nucleus. They're zipping all over the place, but they're staying an average distance away. Okay? So orbitals hold 2 electrons each, and within each orbital, there's 2 electrons, and each electron has a different spin is the word that we use. I wish they didn't say spin because they're not actually spinning, but they're going in different directions. So if there's 2 electrons in an orbital, they're not going in the same direction. Can I do this? They're going like this, right? They're going in opposite directions in this confined space called an orbital, staying some average distance away from the nucleus. Okay, there you go. Now, energy level 1, simplest one, only holds 2 electrons. And those 2 electrons are in 1 orbital because an orbital has 2 electrons. So there's only 1 orbital in the first energy level, and we call it 1s. Why s? I don't know, because they liked s. So s is the name of the first orbital. Energy level 1 only has 1s, which is 2 electrons. Energy level 2, you go to the next average distance out from the nucleus, and it can hold more electrons. There is still a 2s. And by the way, S is a spherical orbit. Maybe that's why they called it S. Probably not. It's probably not that logical. But anyway, it's a spherical orbit. There's somewhere in this ball around the nucleus, okay? The energy level 2 can hold 2 electrons in its s orbital, but there were 8 electrons in the second orbital, or second energy level. So where are the other 6? Well, the other 6 are in these strange things called p orbitals, and we'll get to them in a minute. So here's 1s, right? It's an average distance from the nucleus. It's a ball-shaped orbit, and somewhere in that ball there are 2 energy levels, the 2 electrons, and they're orbiting in different directions around the nucleus. Okay. Now, the p electrons. Oh dear. P electrons are not round. P electrons look like a Q-tip. If you were to take the stick of a Q-tip and cut it out and then take the 2 little puffy ends and glue them back together, that's what a p orbital looks like. It's oblong, it's a sticky outy kind of shaped, and it's mirrored on both sides. And they line up along an axis. Now, axes don't actually exist, but if we were to take a nucleus and put it at the center of a 3-dimensional axis with an x and a y and a z axis, we would find that on x and on y and on z, there are orbitals of 2 electrons each going in opposite directions, and they are an average distance from the nucleus that is energy level 2, right? So we call them 2p. Why p? I don't know. They do. And they call them 2p, x, y, and z to represent that it's on the x-axis, the y-axis, and the z-axis, right? So in energy level 2, there are 8 electrons. 2 of them are in 2s. 2 of them are in 2px. 2 of them are in 2py. And 2 of them are in 2pz. You confused yet? You will be. Okay. Here's a picture. This is energy level 2p. It's not showing the s. The s would be a ball of the same average distance. Okay? But these are just the p's. Energy level 3, you ready for more? Probably not. Here we go. Energy level 3 has 18 electrons. It has 2p, it has 6 in the x's, right? So it has 3s, 3px, 3py, 3pz, and now it has d. Why d? I don't know. Pick a letter, right? So 3d. There are 5 d orbitals. Every orbital can hold 2 electrons, so this must have 10 electrons in it. And it does. Now, these guys, they look like p orbitals, but there's 2 of them. So instead of just like x-axis, now it's like this, right? There's 2 of them, and they can be like this, and they can be like this, or they can be like this, or they can be like this. They're diagonal, and they're double p looking things, which means they have 4 sticky outy blobs, okay? And because they're on diagonals, we named them not just the axis, but the axes that they're between. Sorry. So the d orbitals are called 3d x2, y2, 3d xy, 3d xz, and 3d zy. Dumb names. You don't have to use these names very much. You just have to survive this chapter, okay? After this, you'll just be able to say 2D, 3D, and you'll be okay. The last one is not a P-shaped looking orbital at all. This one looks like a ring and a pole. Strange. God is creative, right? Why make it all the same? Let's stick in this ring and pole thing just because it's fun. Okay, here we go. Here's what they look like. 3, now it still has S and P. And then it also has D, okay? So this is 3dyz, and they call it that because it's diagonal between the y and z axes. This is 3dxz because it's diagonal between the x and z axes. This is 3dxy because it's diagonal between the x and y axes. This one is 3dx2y2, x squared, y squared. It's on the x and the y axis. This is the only one that's not diagonal. It's right on there, okay? And then this is 3dz squared because it's only on z, but then it's got this other one going, I don't get it either. It's okay. Just say, look at that, and move on. Okay. Level 4 has 32 electrons. It has S, it has P, it has D, and it gets a whole bunch more in orbitals called F orbitals. The orientation is weird. Don't even try. Just know that there are a lot more electrons. There's 32 of them, and we've accounted for 18 in SP and D. That means 32 minus 18, 42, 14, 14, 14, yeah. 14 more electrons in the F orbitals. Okay, orientation is weird. Let me just show you a picture so I can tell you I showed you a picture. Here's the S, here's the P's, right? Little oblong things on the axes. Here's the D's, little double oblong things diagonal to the axes. And here's the F's. Holy moly, look at that. And here's their names. Okay, now you've seen it. Praise Jesus. If you put it all together, you get this strange looking thing that looks like a bunch of carnival balloons. All of this to take you to the carnival. Yep, that's what I did. All of these orbitals come zipping out in all different directions, and they're all fighting for space. And remember, electrons are all equally charged. They're all negative, and so they hate each other because negative things are hateful. And so they try to find space where they can be by themselves and not next to anybody else, which is why they all pooch out at different angles and different directions, so that if you put them all together, you get this thing where they're all not sharing each other's space, right? Because that's what they want to do. They're negative, they're hateful, and they come out at all different angles to be as far away from anybody else as they can be. Kind of like, never mind, I won't go there. All right, last concept. When you fill orbitals, you don't just say, is 1 full? Let's move to 2. Is 2 full? Let's move to 3. That would be easy, and this is not easy, so that's not the way it works. Electrons are filled in this diagonal pattern. Now, for right now, look at the diagonal pattern. And in your book, it talks about the diagonal pattern. And see how it works? Look at that little diagonal. We'll walk through it in a second. In just a moment, next lecture, I'm going to show you how the periodic table does this for you. And I think it's much easier to use a periodic table than the diagonal chart, but I feel like you should see the diagonal chart. So I'm going to show it to you now, and then I think I'm going to make your life easier next time we talk. Okay? So look at figure 4-25 in your book, and you will see this pattern. So what happens is we fill the 1s first. It's the first one. Then we fill 2s. And then we fill 2p. And this is making sense, right? Of course. We filled 1, and then we filled 2, and then we fill 3. 3s, right, good. And then we fill 3p. And you're like, oh, well, now we should fill 3d. No. Now we fill 4s. What? I know. I told you. I don't make these rules. And then we go back and fill 3d. And then 3d fills 4p, because we already filled 4s. And then we don't go to 4d, we go to 5s and fill that next. How does this work out? Well, let's pick an element. Let's pick carbon. Carbon has carbon has 6 electrons. So its 1s is full, that's 2. Its 2s is full, that's 2 more. Now we're at 4. And we put 2 electrons in 2p. There's the 6 electrons, right? But if you pick a bigger element, let's say we pick element number 27, okay? Element 27. I fill 2 here, I fill 2 here, I fill 6 here, so now I'm up to 10. Fill 2 here, I'm at 12. Fill 6 here, I'm at 18. Now, I said I was going to do element 27, I've got 11 left. I could put 10 of them here, but I'm not gonna. I'm gonna go put 2 more here in energy level 4s. Then I'm gonna go back, and I'm gonna put my last 9 in 3d. Okay, so this diagonal pattern is how an element fills its energy levels. The periodic table does this for you, and we'll get to that next week. Okay, God bless you. I love you. If you have any questions, I'll see you tomorrow, or you can post them in the comments field below, and I'll try to help you out tonight. God be with you. See you tomorrow.